Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Hello, everyone, and welcome back to the show. We have a truly massive topic on the table today. And I don't mean massive in the casual sense. I mean, we are literally talking about the heaviest, densest objects in the entire universe.
We really are.
We're looking at a paper that just dropped yesterday, February 12th, 2026, in Physical Review Letters.
Yeah, it's about as hot off the press as it gets in this field.
It really is. And I have to say, reading through it this morning, it just felt like one of those moments where you realize we might have been looking at the sky in the wrong way for the last 50 years.
That's honestly not much of an exaggeration. This paper, it's by Hengxi Wang and a team from the Max Planck Institute in Oxford. It takes a problem that has frustrated astrophysicists for decades and it completely flips it on its head.
It really does. It turns a limitation into a tool.
Exactly.
We are talking about the universe's hidden strobes. More specifically, we're talking about supermassive black hole binaries, two absolute monsters locked in a death spiral, hiding in the dark.
And until yesterday, hiding was definitely the right word.
Right. So let's set the stage here for everyone, because I think most people have this image of a black hole as this, lonely cosmic vacuum cleaner floating out there by itself.
A solitary monster.
Yeah, but that's not really the whole story, is it?
Not at all. I mean, sure, solitary black holes exist, of course. But if you look at the grand structure of the cosmos, the whole thing is hierarchical. Galaxies grow by eating other galaxies.
It's galactic cannibalism.
It is. It's a violent, messy history. Our own Milky Way has eaten smaller dwarf galaxies in the past, and we're famously on a collision course with Andromeda.
Which is, by the way, still terrifying. But that's a problem for a few billion years from now, I guess.
Right. But just think about the architecture for a second. We know that pretty much every massive galaxy, including our own, has a supermassive black hole, an SMBH, at its heart.
Ours is Sagittarius A.
Sagittarius A, exactly. Andromeda has one that's much bigger. So when Galaxy A smashes into Galaxy B,
the two big black holes have to go somewhere.
They have to. They don't just, vanish. As the two galaxies merge and all the stars and gas settle down into a new, larger structure, those two central black holes, they have to interact. They sink.
They sink towards the middle of the new galaxy.
Right. Through a process we call dynamical friction, they sink toward the new center of gravity. And so, logic dictates they must eventually find each other.
And form a pair. A binary.
A binary, two supermassive black holes orbiting each other.
And this is the invisible dance we're talking about. The physics says they have to be there. All our models of how galaxies evolve say the universe should be, teeming with these things.
It should be a common phenomenon.
But when we point our best telescopes at the centers of these big merged galaxies, we see nothing.
Well, not quite nothing. We see the galaxy, the bright core. But trying to resolve two distinct black holes that are orbiting closely, it's arguably one of the single hardest observational challenges in all of astronomy.
Okay, but why? I mean, we have the Event Horizon Telescope. We literally took a picture of a black hole shadow a few years back. Why can't we just, zoom in and see two of them?
It's all about scale and resolution. The Event Horizon Telescope was an incredible feat, but it essentially turned the entire planet Earth into one giant radio dish to look at two very specific targets, our own Sagittarius A and the one in M87.
So it's not something we can just point anywhere.
No, not at all. And for these binaries, we're talking about objects that could be millions or even billions of light years away. Now, when they're still very far apart from each other, say a few thousand light years, we can sometimes see them. Okay. We have confirmed cases of dual active galactic nuclei.
So two bright spots in a messy colliding galaxy.
Exactly. You can resolve them as two distinct points of light.
Okay, so we can see the ones that have just started dating.
You could put it that way. They're just waving at each other from across the room. But the ones we really care about, the ones that are gravitationally bound and are spiraling in towards an inevitable cataclysmic merger, those are effectively invisible.
Why? Because they're too close.
Way too close. At that distance, they're separated by less than a light year, maybe much less. To our telescopes, they just blur together into a single blob of light.
So they're either hiding in the glare of the galaxy's core?
Or hiding in complete darkness if there isn't a lot of gas around them for them to eat and light up. And this has created this huge, frustrating gap in our understanding.
A cosmic blind spot.
It is. We see them when they're far apart. And thanks to detectors like LIGO, we can hear them in the final fraction of a second when they actually crash together and merge.
But the whole middle part, the millions of years they spend spiraling closer and closer.
It's a complete black box. We have almost no confirmed observations of that in spiral phase for supermassive black hole.
Which is where this new paper comes in, because the team from Max Planck and Oxford is basically saying, okay, stop looking for the black holes.
Exactly. They're saying stop trying to resolve the dark objects themselves. Instead, look at the background.
Look at the wallpaper.
Look at the stars sitting behind them. They are proposing we use these binary black holes not as targets, but as lenses, as natural telescopes.
Okay, this is where we need to get into the details, because gravitational lensing is a term that gets tossed around a lot. You always hear the same analogy, a bowling ball and a trampoline.
The trampoline analogy, yes.
If that's not going to cut it today, we need to go deeper.
We really do. The trampoline analogy is, well, it's fine for getting the basic idea across, but it completely fails to explain why what this paper is proposing is so groundbreaking.
So walk us through the actual mechanism. Let's start with lensing 101, a single black hole.
Okay. Einstein's general relativity. Mass warps the fabric of space-time, and light, which we normally think of as traveling in a straight line, has to follow the curves in space-time.
So it's not that gravity is pulling on the light, it's that the path itself is bent.
Precisely. Light is just taking the straightest possible path through a curved space. So if you have a massive object, the lens, and a light source directly behind it, the light from that source has to travel around the lens to get to us.
Like water flowing around a rock in a stream.
That's a decent analogy. Now, if you have a single, perfectly spherical mass, like a single non-spinning black hole, that lensing effect is very, very symmetric.
Okay.
And if the alignment is perfect, the background star, the black hole, and you, the observer, are all in a perfect line, that symmetry focuses the light into what we call an Einstein ring.
A perfect circle of light.
A perfect circle. We've seen these. We use them to weigh distant galaxies and find exoplanets. It's a standard tool in the astronomical toolkit.
But what's the catch?
The catch is that word perfect. For a single spherical lens, it has a single focal point. You have to be exactly on that line of sight to get that extreme magnification to see the ring. It's like a laser beam.
So if a background star is just a tiny bit off to the side of the black hole, we don't see the ring.
You'll see some distortion. The star might appear as two separate, slightly brighter images, but you don't get that massive, massive spike in brightness unless the alignment is just so. It's rare. Very rare.
Okay, that's lensing 101. Now, enter the second black hole, lensing 202.
This is where everything changes. You aren't just adding a second lens next to the first one. You are creating a complex interference pattern between two deep gravitational wells.
The paper uses this term, caustic curves. And I know caustic usually means something that burns.
It does. But in optics and in gravitational lensing, it means something else. Let's go back to that swimming pool analogy I mentioned earlier.
The squiggly lines on the bottom.
Exactly. Think about why those lines are there. The surface of the water isn't flat. It's covered in little waves and ripples, right? Each ripple acts like a tiny, imperfect lens.
Okay, I'm with you.
So these ripples aren't focusing the sunlight into lots of little single points. They're focusing the light into lines, into curves. And those bright dancing webs of light on the bottom of the pool, those are the caustics. It's where the light rays pile up, where the intensity is highest.
Got it. So the water ripples are the imperfect lens, and the bright lines are the caustics.
You've got it. Now, take that concept and scale it up to the cosmos. Instead of ripples on water, you have two supermassive black holes orbiting each other. Their combined gravity creates a very complex surface in space-time. It's not a smooth bowl anymore.
It has ridges and valleys.
Exactly. And those gravitational ridges focus the light from background stars not into a point, but into a network of high magnification lines. Those are the caustic curves.
And what do they look like?
For a binary system, this network creates a very specific shape. The paper describes it as a diamond-shaped structure. In mathematics, it's called an asteroid.
An asteroid, like the old video game.
Spelled differently, but yeah, it looks a bit like that. It's a star shape, a diamond with 4 points, but the sides are curved inwards. They're concave.
So let me picture this. Floating in empty space. behind these two invisible black holes is this other invisible thing, this geometric diamond of pure magnification.
That is exactly what it is. And here is the absolute critical difference between a single black hole and a binary.
Okay.
For a single black hole, the region of very high magnification is a tiny point. For a binary, the region of very high magnification is this entire, much larger diamond-shaped perimeter.
So the target is just bigger.
Massively bigger. Benz-Coxis, one of the authors, makes this exact point in the press release. The chances of a background star's light being hugely amplified increase enormously for a binary compared to a single black hole.
It's the difference between trying to hit the bullseye with a single dart and just trying to hit any part of the dartboard.
A much, much bigger dartboard. You've gone from trying to thread a needle to trying to hit a barn door. The probability just skyrockets.
Okay, so the net is bigger. We have a much better chance of a background star lining up with this diamond shape. But the black holes aren't just sitting there.
No, they're not. And this is where the strobe concept finally clicks into place. If the two black holes were just frozen in space, the diamond caustic would be frozen too. A star that falls on it would just look like a permanently distorted, brightened image.
But they're not frozen. They're orbiting each other.
They're orbiting. They're in a constant dance.
So the diamond spins.
The diamond spins. It rotates right along with the binary. Imagine a lighthouse, and the beam is rotating. But in this case, the beam isn't a simple ray of light. It's this entire complex caustic structure. It's a diamond-shaped beam of magnification.
And that beam is sweeping across the background sky.
Constantly sweeping. And the background sky, even in a seemingly empty patch, is just filled with faint, distant stars.
So it's only a matter of time before that sweeping line of magnification runs over one of those stars.
It's inevitable. Purely by chance, the caustic curve will cross a background star.
And when it hits,
Yeah.
what do we see?
We see a flash. The mathematics of the caustic means the magnification just shoots up. Hanxi Wang, the lead author, describes it as an extraordinarily bright flash. For a brief period of time, it could be hours, could be days. It depends on the geometry and the speed. That background star will suddenly become hundreds or even thousands of times brighter than it normally is.
Like someone switched on a cosmic light bulb.
A very powerful one. And then, as the caustic line passes over the star and moves on,
The star goes back to normal.
it fades back to its regular, faint baseline brightness, as if nothing happened.
But the binary is still orbiting
The binary keeps spinning, so the diamond caustic comes around again.
on the next orbit. And if that star is still in the path,
It hits the star again.
flash.
Flash.
So we get a repeating signal, a blink.
You get a strobe light, a repeating, predictable burst of starlight, all caused by two invisible objects dancing in front of it.
Okay. I had to play devil's advocate here. You know I love this idea. But the universe is a really noisy place. It's full of things that blink and flash. We have variable stars, Cepheids, flare stars, cataclysmic variables, supernovae. I mean, the list goes on. How can we possibly be sure that a blink we see is from this weird lensing effect and not just, a star having a hiccup?
That is probably the most important question in this entire field of time domain astronomy. Is this transient, this flash, unique? And the authors of this paper argue that, yes, this signal is remarkably distinct. It has a fingerprint.
Distinct in what way? The timing, the
But
color.
shape. It all comes down to the light curve. That's what astronomers call a plot of an object's brightness over time.
Okay.
So if you look at the light curve of a typical variable star, like a Cepheid, it often looks like a smooth wave. The brightness swells up and then it shrinks back down. It's often quite symmetric. That's because the physics is internal to the star. It's literally breathing, expanding, and contracting.
And a caustic crossing. What did that look like on the graph?
It looks nothing like that. A caustic crossing is purely geometric. It's not about stellar physics, it's about the geometry of crossing a fold in space-time. The light curve is sharp, it's asymmetric.
Asymmetric, yeah.
You get a very, very sharp rise in brightness and then a slightly slower fall. The peak is less of a gentle curve and more of a spike. The math predicts a very specific U-shaped profile right at the peak. It's a fingerprint that just doesn't look like anything a star does on its own.
So if we see that specific jagged spike shape, we know we're looking at gravity, not chemistry or fusion.
That's the idea. And there's another layer to it. It's not just periodic. The paper calls it quasi-periodic.
Quasi-periodic, so almost repeating.
It repeats, but not perfectly. And the reason it's not perfect is the most exciting part. It's the very thing we've been trying to measure for decades.
The in-spiral.
The in-spiral. We should probably pause here and really dig into why these black holes are merging in the first place. We mentioned dynamical friction earlier, how they sink to the center. But that process isn't perfect. It leads to a famous problem.
The final parsec problem. I remember this one. It's the idea that they get really close. And then they just get stuck, right?
Exactly. Dynamical friction works great when the black holes are far apart, moving through a dense sea of stars. They transfer their orbital energy to the stars and sink. But once they get close enough to form a tight binary, they clear out their neighborhood.
They kick all the nearby stars away with gravitational slingshots.
Right. And once they've kicked all the nearby stars away, there's nothing left to create that friction. There's nothing left for them to transfer their energy to. So, in theory, they should just stall. They should orbit each other forever at a distance of about a parsec or a few light years. They should never get close enough to merge.
But we know they do merge. We hear the gravitational waves from stellar mass black holes merging with LIGO all the time.
Exactly. So something has to bridge that final parsec gap. For a long time, we weren't sure what it was. Maybe friction from a big gas disk, maybe interactions with a third black hole. But for these really massive binaries, the dominant force that brings them together in the end is the emission of gravitational waves.
And this is the key to decoding the strobes.
This is the Rosetta Stone. As these two huge masses whip around each other, they are constantly churning space-time, radiating enormous amounts of energy away in the form of these gravitational waves.
And if they're losing energy,
their orbit has to shrink. As the orbit shrinks, conservation of angular momentum means they have to speed up.
And if they orbit faster, the strobe light blinks faster?
Precisely. This is the decoding part of the whole thing. If we can find one of these systems and watch the flashes over time, we aren't just seeing a blink. We are seeing a cosmic clock that is ticking faster and faster and faster.
So we can literally measure the rate of orbital decay just by timing the flashes from a background star.
Yes. We can watch general relativity happen in real time. But the paper points out something even more profound, even more subtle.
What's that?
The emission of gravitational waves doesn't just change the orbital period. It actually changes the shape of the caustic diamond itself.
Wait, what? How?
Yeah.
The waves themselves are distorting the lens.
In a way, yes. The loss of energy and the shrinking separation between the two black holes alters the overall gravitational potential of the system. This, in turn, subtly alters the geometry of the caustic curve. The paper states that it imprints a characteristic modulation on the flashes.
So the lens itself is warping as the orbit decays.
In cosmic real-time, yes. So maybe the peak brightness of the flash gets a tiny bit higher with each pass, or the U-shape of the light curve gets a little bit wider. The timing between the flashes will shift in a very specific, predictable way that is a direct signature of gravitational wave emission.
Let me see if we got this straight. We find a star that's flashing. We check the light curve and confirm it has that jagged, asymmetric shape of a caustic crossing. We watch it repeat. From the time between the flashes, we get the orbital period. From the brightness and shape of the flash, we can work out the total mass of the binary.
And their mass ratio, yes.
And then, from the tiny change in the timing and the shape of the flashes over years, we can measure how fast they're spiraling in.
You've got it. It's a complete telemetry package for an invisible system. We can extract the masses of the black holes, their distance from each other, their orbital speed, and the exact rate at which they are falling towards doom.
That's mind-blowing. It's like finding the black box of a plane crash months before the plane actually crashes.
That's a grim but surprisingly accurate analogy. We are watching the slow-motion collision.
But we have to talk about timescales here. Because in astronomy, slow motion usually means check back in a million years. If a big binary has an orbiter period of, say, 5 years, do we have to wait a whole career to see the orbit change?
That is the practical challenge, yes. For the most massive, supermassive black holes, we're talking billions of solar masses, the orbital period in this phase could be a few years. So you see a flash, and you set a reminder on your calendar for 2031.
And 5 years later, flash.
Hopefully.
Yeah.
So for any single system, yes, it's a very slow accumulation of data. But the real power of this method isn't in staring at one system forever. It's in watching all of them.
A population study.
Exactly. The paper really emphasizes this point. They say, what is possible are snapshots. Think of it like walking into a forest. You can't just sit there and watch a single acorn grow into a mighty oak tree. That takes a century.
But you can look around and see an acorn on the ground, a little sapling over there, a young tree, and a huge old one.
And a rotting log, exactly. By piecing together all those different snapshots, you can understand the entire life cycle of the tree.
So we apply that to the sky. We look for these flashes everywhere.
everywhere. And if we scan the whole sky, we will find binary black holes at every single stage of this in-spiral process. We'll find some that are widely separated, flashing every decade or so. We'll find some that are tighter and faster, flashing every few months. And we'll find some that are right on the brink of merging.
And by putting all those data points together, we can build the movie of how these things evolve.
We can finally fill in that massive gap in our knowledge of galaxy evolution.
Which brings us to the tools. Because to scan the whole sky and catch a random flash that might only be visible for a few days, that just sounds incredibly expensive. Like we'd need a new dedicated telescope.
And it would be if we weren't already building the perfect machines to do it for other reasons.
This is the part I love. We don't need a new line item in the federal budget for this.
No. We can just piggyback on the next generation of survey telescopes that are about to come online. The paper specifically calls out two of them, the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope.
Let's talk about Rubin first. That's the one down in Chile, right? The one that used to be called the LSST.
That's the one, the Legacy Survey of Space and Time. Rubin is an absolute beast of a telescope. It's not like Hubble or the James Webb. Hubble is like a sniper rifle. It stares at one tiny, tiny patch of sky with incredible detail. Rubin is a wide-angle lens. It's a shotgun.
It takes a picture of the whole sky.
It will photograph the entire visible southern sky every 3 or 4 nights, over and over and over again, for 10 years straight.
I can't even comprehend that amount of data.
It's something like 20 terabytes of data every single night. It is literally creating a high-definition movie of the night sky.
So if a background star behind a binary black hole flashes on a Tuesday night and then goes back to normal by Friday,
Rubin will see it. It is designed from the ground up to find transients, things that change, things that flash, things that move, supernovae, asteroids, variable stars.
And now, thanks to this paper, binary black hole strobes.
So on the list of targets now, the data will just be sitting there in the archive.
So it's not an observational problem, it's a data science problem.
Exactly. The photons will hit the detector. The challenge is writing the sophisticated software, the algorithms, that can sift through those petabytes of data and automatically flag it. To have a program that says, hey, wait a minute, that little blink in sector 7G, that has the asymmetric caustic light curve, flag it for a human to look at.
And what about the Roman Space Telescope?
That's NASA's next great observatory. It's space-based, so no atmosphere to worry about, and its key feature is its field of view. It can see a patch of sky 100 times larger than Hubble can in a single pointing.
So it's like a Hubble-quality shotgun.
That's a great way to put it. It's doing what Rubin does, but from space and in the infrared. So between the two of them, we're going to have eyes on almost the entire sky, almost all the time.
We're really entering a new era of astronomy.
It's the golden age of time domain astronomy. For most of human history, the sky was static. We took a photograph. Now we're watching the video.
I want to pivot for a minute to what you might call the competition, or maybe the partnership. We mentioned LIGO before, but there's a future mission that's specifically designed for these supermassive systems. LISA,
the Laser Interferometer Space Antenna.
It's still just the coolest acronym in science.
It really is. LISA is, it's essentially a gravitational wave observatory in space. Imagine 3 separate spacecraft flying in a perfect triangle formation, millions of kilometers apart from each other.
And they just shoot lasers at each other.
They constantly shoot lasers at each other to measure the distance between them with unbelievable precision. When a gravitational wave from a supermassive black hole merger passes through the solar system, it will stretch and squeeze the distance between those spacecraft by less than the width of an atom.
And LISA can detect that.
LISA will be able to detect that. It's designed specifically to hear the low-frequency hum of these supermassive black hole binaries as they spiral together.
So LISA hears the gravitational waves, and this new method sees the light from the strobes.
Right. But here's the timeline issue. LISA is not scheduled to launch until the mid-2030s. Maybe 2035, 2037, somewhere in there.
So we have a decade-long gap.
We have a gap. And this is where the new lensing method claims a huge, huge victory. In the paper, Cox calls it an extremely exciting prospect. Using Rubin and other telescopes, we can detect these in spiraling binaries with the strobe method years before LISA ever gets off the ground.
We can build the catalog of targets now.
We can find them. We can map them. We can say, okay, at these coordinates in the sky, we have a binary with a mass of 1 billion suns and a 2-year orbital period. We can build a watch list.
And then, in the 2030s, when LISA launches,
We turn it on, and we already know where to listen. And this opens the door to the holy grail of modern astrophysics. Multi-messenger astronomy.
That's a buzzword I hear constantly. Can you break that down for us?
It just means observing the same cosmic event with more than one messenger or more than one sense, seeing it with light and hearing it with gravitational waves. Think about watching a thunderstorm. You see the flash of lightning. That's your light signal. That's the strobe. A few seconds later, you hear the boom of the thunder. That's your second signal.
And from the delay between the two, you know how far away the storm is.
Exactly. If you only have one, you have incomplete information. But if you have both, you can learn so much more. Now, apply that to black holes. If we can see the flash from the caustic and hear the gravitational hum from the inspiral coming from the same object at the same time, we can test fundamental physics in ways that are currently just science fiction.
Like what? What's the first thing you'd test?
The speed of gravity. Einstein's theory says gravitational waves travel at the speed of light, but do they? Do they really? To the 15th decimal place. If the flash and the wave arrive at our detectors at slightly different times after traveling for 1 billion years, that could mean Einstein was wrong.
Which would be a Nobel Prize.
Instantly. We break physics as we know it.
Wow. And it would also tell us about the environment around the black holes, wouldn't it? Because light gets affected by gas and dust, but gravity.
Gravity just plows right through everything. It doesn't care. So if the light signal is a little bit delayed or scattered compared to the pristine gravity signal, it tells us exactly how much messy stuff, gas, dust, accretion disks is sitting around the binary. It gives us a complete picture.
It really feels like we're moving from just guessing about these systems to being able to put them on a lab bench and measure them.
That's the transition the whole field is making. We are moving from purely theoretical models of binary evolution to direct observational telemetry.
I want to circle back to something you mentioned earlier about the background, the stars.
Okay.
For my whole life, I've thought of the background stars as, well, as just noise. They're just the wallpaper. They're the things you have to subtract from your image to see the galaxy you're actually interested in.
Astronomers have a term for it, the confusion limit. When there are so many faint stars, you can't distinguish your target from the background. It's just stuff in the way.
But this paper just completely inverts that idea. It says the background stars aren't the noise, they're the tool.
They are the screen. That's the best way to think about it. The binary black hole is like an invisible film projector. It's projecting its gravitational shape, this spinning diamond, out into the universe. We can't see the projector itself.
But we can see the image it's casting on the screen at background stars.
Exactly. We see the flash as the beam sweeps past. The universe is a cinema, and we're finally figuring out where to look to see the show.
I want to end on a thought that really struck me when I was reading the discussion section of the paper. And it's about old data, archival data.
Ah, yes. The potential for data archaeology.
We've been taking digital pictures of the sky for a long time now. The Sloan Digital Sky Survey, Pan-STARRS, a dozen other projects. We literally have petabytes of images stored on hard drives and server farms going back decades.
We do, a treasure trove of information.
And if these invisible caustic curves are constantly sweeping across the sky all the time, everywhere,
Then they have, without a doubt, triggered flashes that we have already photographed.
we've already seen them. We just didn't know what we were looking at.
Statistically, it's almost a certainty. We have very likely recorded these exact events.
So why didn't anyone notice?
Because if you're looking at an image from 1998 and you see a faint star that for one night was 100 times brighter, and then in the next image it's gone again, what do?
I assume it was an error.
You'd shrug. You'd call it a cosmic ray hitting the detector, a glitch in the CCD chip, an anomaly. You'd discard it because it doesn't fit any pattern you know. It's a one-off weirdo.
We didn't have the dictionary to translate what we were seeing.
We didn't know the language. We didn't know that a jagged asymmetric spike was the signature of a binary supermassive black hole caustic. We just filed it under noise.
But now,
Now we have the template. Now we can write new algorithms to go back into all that old data from Sloan, from Pan-STARRS, and specifically hunt for that unique light curve shape.
so the very first discovery of one of these binary black hole stribes might not happen with the Rubin telescope in 2027. It could happen on a supercomputer next week, sifting through data from 2015.
That is entirely possible. The evidence could very well be sitting there gathering digital dust on a server rack somewhere. We just need to blow off the dust and look at it with these new eyes.
That, to me, is the most exciting kind of science. The treasure hunt where you realize the map leads back to your own basement.
It's a fantastic reminder that data is never truly dead. It just waits for a new theory, a new idea to bring it back to life.
Well, I think that is a perfect and very hopeful place to wrap things up. We've gone from invisible monsters to diamond-shaped lenses to cosmic strobes and finally to diving for treasure in old hard drives.
It's been quite a journey.
It really has. And for everyone listening, the next time you look up at a star and you see it twinkle, well, okay, it's probably just the Earth's atmosphere. But somewhere out there, a star is blinking for a much, much grander reason, because two giants are dancing in front of it.
Keep watching the data.
Thanks for listening, everyone. We'll catch you on the next one.